Okay, I'm looking at page 31, second case 2, right? Case 2. Okay, how do we expand the number of words? Okay, expand the number of words. Yeah. So basically, right, now the data lines remain the same. Okay, now remember your data. Can I ask your data line is bidirectional? Don't forget.
Yes.
Data are bidirectional. How about address? Yeah, you remember?
Data go both ways.
Yes, data is bidirectional. Okay, bidirection. This one is uni. Okay, unidirection. Okay, one direction. So I'm just showing you here. Of course, you can look at your figure on page 31, right? Yeah, it's much clearer there. Because they draw the lines. So typically they draw like that. Okay. How many data lines by the way? 4. So yeah, correct. So you can draw and then connect. Okay, you can draw attach here, right?
Yeah,
attach here. Don't worry, you will not be asked to draw. Okay. So this one is what kind of combination is this? It's in parallel. This one is connected in parallel.
16
Okay. No, what we want is to achieve 32 times 4.
No, this is still 4.
Still 4. Your data is no change. Okay. Now do remember. You see, okay, can you sidetrack a bit? Can you look at page 32, that table? That's very important. Okay, now how do we achieve 32 combination? Correct, 2 to the power of 5. Very good. Okay, now the question what they want is they want to have 32 combination. At least 32 address combination. Address combinations. You know what I mean? So which means that if I draw the memory map, okay, if I need to now I know it's not easy this one because I'm trying to switch you from physical to the memory, then switch you back again. So it's not easy. You have to try to visualize it. Not easy. Okay, now what I want is 32 combinations. How to get 32 combinations here? How do I get 32? Obviously, right? To the power of n, you all know very well. Right, I need to get 32 combinations. So what is the n? 5, correct. So which means that somehow or rather I need 5 lines here. Yeah. I definitely need 5. Now I cannot achieve 32. Okay, now because you all just rightfully told me 2 to the power of 5. So I must have 5 physical lines here.
Where at the address?
Yes, address, correct. I need 5 physical unique lines. But of course I need to have 32 unique addresses. Addresses are unique. Remember, this one is unique. Each address, each memory address is unique. Okay, which means that somehow or rather I need 32 of these physical memories location. 32. Okay, in order to achieve that, I'm going to use 5. I need 5 physical lines. A4, A3, A2, A1, A0. Right? 5 lines, agree? So therefore I can generate this one. Right?
So that's where the inverter comes in.
Later I will explain it. Okay, of course I can keep on writing until you see 1, 1, 1. Am I right? This time keep going. 32 combinations. So each of these is a memory space. Each one of these cell here, okay, is a memory location. Okay, memory location which is unique. How many data are inside? 4 lines. Now this time is 4 because my requirement is 32 by 4. Okay, so I'm quite safe to say that inside, right, this memory, I got 4 bits. 4 bits. Okay, I might represent it as D, what did they use? D3, is it? Doesn't matter, they call it D3, yeah? DB, yeah?
DB0.
DB, DB means data bus, but to me it's just a data. So I call it D3, D2, D1, right?
3210.
Yeah. Okay, is that clear? Up to here, D0. Okay, but the main thing is you must be clear is that I need 32 combinations, which means I need 5 address line, physical lines, to generate this combination of 32. Okay? But now the challenge is this, you are given a 16 by 4. Which means that each memory chip can only go up to half only, isn't it? 16 by 4. 16 by 4. But then how do I break it into 2? So that is 16 and then another 16. That's what I'm trying to drive at. So somehow, this thing, right, this memory map has to be divided into 2, sliced into half. Okay, so maybe one of the RAM here, one of the RAM chip, each take half. Each of them take half. So what did they say there? Okay, they say you use maybe the 0 for the first half. So I call this RAM 0. The reason why is this very simple. You have 5, look at this one. The clue is here. Now this table, how are you going to generate this combination? This bit will be not changed, right? The most significant bit here, A4 bit. Will it change? When will it change?
After
the 17, right? If you think very carefully, this combination...
the 17 one
yes, very good. You can see it. What happens is this. Let me just make it slightly clearer for you here. Okay, I hope. Okay, now what you can, of course, do is this. Okay. Now you can see that I can just keep on doing this. Can you see behind? Yes. Can you see? So this one will toggle, right? Of course I can keep writing, but it's going to take me a long time. Agree? So this one will keep going, right?
Until all 0, then the rest all 1.
This is 1, right?
One 0, then the rest.
Is it correct? Of course keep going, or this one will keep. But do you notice this one don't change?
Until the 17 one.
Right. You notice that this part here, what is the uniqueness?
Is the first, the 0
This is the, if I call it the most significant, right? Most significant digit or bit if you want MSB. This is like my MSB. Okay, now this thing from here to here will not change. From 0 all the way until 15, right? It will not change. But on the 16 count, right? 16 count, it will switch. Switch to the next one, because once it hits, once I'm going to just extend a bit. Once you hit this point, 1 1 1 1, right? What's the next thing that you'll do?
1
or 0.
Yes, this one will flip, right?
Yeah.
Okay. Yeah, so we are leveraging on this to do the selection of between the 2 chips. You see, so that this fella take half, the other fella take half. So that's what I mean. So you take half here, then you take another half. Half. Make sense?
Can you repeat the previous 3?
Which one? Backtrack. So up to this point, do you understand? A4 to A0, right? You can generate these 5 bits, right? So they have this combination, right? 001, 010. This one you know, right? Up to this point where you will start to transit to the next part, because the next one is going to flip. It's going to this one trigger to 1, right? Am I right?
Yeah.
We are capturing this point here. You see? This point, because this point onwards, this bit will be stay at 1. Ruben, do you see? This one will stay at 1 all the way until you see the final one, 1 1 1 1, all 5 ones. See, catch this transition. Then you understand what I'm trying to do here. I'm using this to segregate these two. Segregate means slice into two, half. I want half here. So that this memory chip will help me take care the address. Okay, 0, 0, 0, 0, 0. 5 of these, right? Actually not 5, because you are using this one to do the select. Now to answer Siwoo, just now your question, right? You were asking me why on page 31, can you look at your figure? You see this page 31 figure, see very carefully. Page 31, right? This figure here, you will notice that the A4 line, A4 line is connected to this chip select. It's basically to handle this one, the switch. Okay, for those of you who can see it, this one, right, is tied to here. Okay, so that when it's 0, which chip is enabled? Can you tell me if this is RAM 0, this is RAM 1. When this is 0, right, logic 0, because there is an inverter here, remember? Lisa, do you see? You see? So when it's 0, do you enable this one or you enable this one? This one, right? Because this one is active low. 0, I activate this memory. I work on this part first. Because 0 on this end here is going to convert logic 0 to logic 1. So logic 1, what happens? This will be not selected.
There's a bubble there.
There's a bubble here, right? Yeah, correct. But this is active low. I told you. So 0 will activate this chip. You all see. So that when it's 0, it will activate this RAM only. Because 0 on this end is inverted to logic 1. 1 will disable this chip. Okay, slowly. 0 come here, inverted to logic 1. 1 will disable this chip. Okay, but this one is fine because 0 here is already active low. There's a bubble there. 0 will activate this chip, but 0 here will disable this chip.
So when it hit 1, then it will go.
Yeah, then it's vice versa, flip flop. If it's 1, because once you hit the second half, right, you're gonna activate the other half of the chip. Then you disable the top one, which you disable this one. So I know it's not easy because now I need to switch you between the memory map to the physical thing. Then I switch you back and forth, so you can get confused. But take it slow.
Why you need 5 addresses to do this? Why you cannot just use 4?
Cannot, because the requirement is that I need 32 combinations. That's the requirement. I need 32 by 4. 32. But I'm given this. Of course, if you say I buy 32 by 4, then you solve the problem. But this is the theoretical question for you to think, is it? Of course, I can buy this one, right? Sure, and solve the problem. I don't need to worry about all these things. Of course, if you buy this one, it's better, definitely. Yeah, I mean, I'm sure, of course, when you have something, right, and the original thing is always better than something that is being like chipped off, then you put super glue, right? Of course, like, in a way.
Okay. For this case, right, then they ask how many you need. Then you just write 2. Then
you need to explain it. I think.
Oh, you don't need explanation.
You need explanation. Yeah, correct.
Okay.
I don't know whether the past exam got asked this type of question or not, but let's take a look.
Never. It's just that one only case 1 and case 2 only.
Oh, you're lucky lah. Okay, let me take a look. Pause this one first.